In this lecture, we're going to move into the 17th century and look at the most important function to be discovered since the trigonometric functions, namely the logarithm and also the exponential function. Exponentials were certainly dealt with before the 17th century, but as a function, that really only begins in the 17th century. But before I start to look at logarithms and exponentials, I need to back up a bit into the middle of the 16th century and look at what was happening in astronomy, because that would directly influence what would then happen in the 17th century. 1543 is the year that Nicholas Copernicus published his groundbreaking work on the revolution of the heavenly spheres. Copernicus was a Roman Catholic monk in Poland, and he was trying to understand the motion of the planets. And in particular, he was very disturbed by this problem of retrograde motion, this apparent backward motion of the planets at certain times. And if you recall back when we looked at astronomy in ancient Greece, this was one of the problems that Archimedes raised, and a number of different Greek scientists, astronomers, looked at this problem. And one of them was Aristarchus, who suggested that what was happening was that the Earth was actually going around the Sun, and that would explain this retrograde or backward motion of the planets. The problem with that explanation of Aristarchus was that we have absolutely no sense of a motion of the Earth. It appears that the Earth is stationary. And so that was quickly dropped in favor of a slightly later explanation that came from Apollonius of Perga, the same Apollonius who did the important work on conics. And it's Apollonius who came up with the idea of epicycles, that in fact the Earth is stationary at the center of the universe. And what is actually happening is that the planets are traveling around the Earth on little circles whose centers then travel around the Earth. And this would become the foundation for what was known as Ptolemaic astronomy. Certainly there were many Greek astronomers before Ptolemy who established this system, but Ptolemy really showed how you could model the movement of the planets using these epicycles. And over the succeeding centuries, the system became more and more complicated because whatever system was in place never really matched what people were observing in the heavens. And so they tried the idea of equants. They tried putting epicycles on epicycles. They got very complicated models. And what Copernicus decided to do was to simplify this process, or try to simplify the process, by going back to the idea of Aristarchus and postulating that it was, in fact, the Earth that goes around the Sun, rather than the Sun that goes around the Earth. The problem with Copernicus's work is that he also assumed that everything went around the Sun in a circle. And observations were sufficiently accurate by this time, the mid-1500s, that simply did not accurately predict where the planets should be. The planets weren't where they were supposed to be if, in fact, they were traveling in nice circles around the Sun. And so a number of astronomers began to try to improve on this model and figure out what was really happening. Something else with Copernicus is that in his book on the revolution of the heavenly spheres, actually, he probably did believe that the Earth moves, but he simply puts it forward as a hypothesis, as a possible model. But succeeding astronomers began to suspect that maybe, in fact, the Earth is moving around the Sun. But what was needed were much more accurate observations of the positions of the planets on which a better model could be built. And the person who undertook to find these observations was a Danish astronomer by the name of Tycho Brahe, born in 1546. He would die in 1601. He was a very wealthy nobleman. It's actually been estimated that at one point he personally owned 1% of all of the wealth in Denmark. And he set up an astronomical observatory on the island of Hven. It's just off the coast of Sweden, actually between what is now Sweden and what is now Denmark, although at that time what is now southern Sweden was part of Denmark. Brahe had studied astronomy in Copenhagen. He had then gone to Germany to continue his study of astronomy. While in Germany, he engaged in a duel where his nose was sliced off. And rather unfortunately, he went through the rest of his life with a tin nose, something that makes him very distinctive. We know that he also studied medicine and alchemy. He made two important observations in his observatory in Hven. The first, 1572, was a careful observation of a supernova. So a star suddenly becomes a brilliant light in the sky and then disappears. And Brahe observed this. And one of the things that this showed is that, in fact, the stars in the heavens are not eternal. They can appear out of nowhere. They can disappear. And so this began to undermine the Aristotelian view of the heavens. Something else that Brahe observed in 1577 was a comet. Now, if you really believe that the heavens are perfect, you can't have anything moving through the heavens. It was believed up until that point that comets were actually something that happened within the atmosphere of the Earth. And Brahe did very careful observations and measurements of the position of this comet. And he was able to show definitively that the comet, in fact, was well beyond the reach of the moon. It was well outside the atmosphere of the Earth. And so it really was moving through the heavenly rain. Brahe, you must remember, was working before the time of telescopes. And so all of the observations that he was making were being made simply by the naked eye with very accurate instruments to line things up, but without the aid of a telescope. Now, the best you can normally hope for in this case is to get an accuracy of about 2 minutes of arc. So 360 degrees is a full circle, and 1/60th of a degree is a minute. And actually, if there are two stars in the sky whose difference is less than 2 minutes of arc, it's very difficult to tell them apart. So that's normally about the best you can do with naked eye observations. Brahe actually was able to push that a little bit further. Looking back at his records, we now realize that sometimes he was able to get the position of the planets down to within half a minute of arc, very often within 1 minute of arc. But he had these incredibly accurate observations. In 1599, he was hired by the Holy Roman Emperor of the time, Rudolph II, whose capital was in Prague, to be the court astrologer. And as I mentioned in earlier lectures, there really at this time was no difference between a mathematician, an astronomer, and astrologer. So Brahe, as an accomplished astronomer, would also have been much sought after as an astrologer, trying to predict the position of the planets and interpret what that actually meant for what would go on Earth. And shortly after he became court astrologer, he hired a young assistant, Johannes Kepler. Kepler had been born in 1571. Shortly after Kepler became Brahe's assistant, Brahe died. And there was a story circulated at the time that the reason that he died was that he was at a banquet with the emperor, and he desperately needed to relieve himself, but being seated at table with the emperor, he could not simply get up and leave the table until the emperor was ready to get up and leave the table. And the story was that his bladder burst and he died of the infection. Well, about 50 years ago, Brahe's corpse was exhumed and examined, and I'm not sure how much of his bladder was left at that point, but they did an analysis of his hair and discovered that, in fact, he had died of mercury poisoning. Now, this raises all kinds of suspicions, because in fact Kepler benefited greatly from Brahe's death, and it has been suggested that perhaps Kepler had a hand in doing in Brahe. Kepler inherited Brahe's position as court astrologer to Rudolf II, and he also inherited all of Brahe's very valuable data. And it became Kepler's life work to take this meticulous data and try to find a model that would fit it. And Kepler eventually would succeed in doing this, but to do it he needed to do very extensive calculations, very involved calculations. Eventually he would come to the realization that the reason that Copernicus was off is that the orbits of the planets are not circles, they are actually ellipses. They're ellipses not with the sun at the center of the ellipse, but with the sun off at the focus of the ellipse. And so he realized that the data that Brahe had collected could be explained with this model. Kepler came up with other rules, other laws of celestial motion. He realized that the planets sweep out equal area in equal time, and practically what this means is that the planet speeds up as it comes in close to the sun, and then it slows down as it moves away from the sun. So it's not always traveling at the same speed. And another one of Kepler's laws is that the square of the time that it takes to complete an entire revolution is proportional to the cube of the average distance to the sun. Now, Kepler came up with many other laws. In many respects, he really was an astrologer and a mystic. He explained the relative distances of the planets in terms of Platonic solids, each one sitting inside another. He also talked about the way in which the crystalline spheres that the planets were embedded in would rub against each other. And he talked about the music of the spheres, and he actually describes the kinds of harmonies that the planets make as they travel around the sun. But I want to get back to his question of trying to work with building this model by doing these very involved calculations. With the kind of data that he had inherited from Brahe, Kepler needed to be able to do calculations that were accurate to 5 digits. And in fact, shortly after Kepler began doing his work on Brahe's data, the telescope was invented. Galileo would be the first person to actually begin to use the telescope to look at the stars, and this happened very early in the 1600s. Kepler then would begin to get even more accurate data. Very quickly, he needed not just to do 5-digit calculations, but 7-digit calculations. And certainly by 1630, the data that was available coming from the telescopes was sufficiently accurate that people needed to be able to do calculations that maintained 10 digits of accuracy. Now, doing multiple multiplications and divisions and evaluating trigonometric functions to 5 or 7 or 10 digits of accuracy is extremely difficult. And so a computational device was needed in order to make this easier to do. And that computational device would be invented by the Scotsman John Napier. Napier was born in 1550. He was a Scottish nobleman. He was the Laird of Merchiston in what today is now part of Edinburgh. And he had many interests. He was interested in theology. One of his famous works was published in 1593, and it was a diatribe against the Catholic Church called The Plain Discovery of the Whole Revelation of St. John, in which he talks about how the revelation of St. John is really describing the Pope as the Antichrist. But despite this great skepticism of the Catholic Church, he did travel to Italy in 1594. It's very possible that he actually met Galileo at that time. But he clearly came back from Italy with an interest in developing these computational tools for making it easier to do multiplications and divisions. And in 1614, he finally published his work, what he called Description of the Wonderful Canon of Logarithms. Now, the word logarithm is a word that was invented by Napier to describe what he had created, and there are various ways of understanding its etymology. You can actually see its root in the phrase ratio number, which is a reasonable explanation for what's going on with a logarithm. But the etymology that I really like is to take logarithm as being composed of two Greek words, logos and arithmos. And if you recall back when I was talking about Greek mathematics, I said that they viewed mathematics as two different areas. One was logos, or logical mathematical reasoning, and the other was arithmos, from which we get our word arithmetic, and this is calculation. And the beauty of the logarithm is that it applies this logical mathematical reasoning to the problem of calculation. And that's precisely what Napier was getting at, trying to simplify calculations. And the idea behind the logarithm is to exploit what happens when you're working with exponents. So let me give you a simple example. Let's say that I want to multiply 16 times 128. Well, if I know my powers of 2, I know that 16 is 2 to the 4th power, and I know that 128 is 2 to the 7th power. Now, one of the results that the Islamic mathematicians were certainly very well aware of and was now known in Western Europe is that if I want to multiply 2 to the 4th times 2 to the 7th, I can accomplish that by adding the exponents. 2 to the 4th times 2 to the 7th, that's 4 copies of 2, times another 7 copies of 2, I get 11 copies of 2. 4 plus 7 is 11. And if I know my powers of 2, I can simply read off a table. 2 to the 11th is 2048. Well, that's great if I'm trying to multiply 2 powers of 2. What if I want to multiply 19 times 33? Well, it is possible to write 19 as a power of 2. You can work with fractional powers of 2. 2 to the 1/2 power is the square root of 2. 2 to the 5/3 power is 2 to the 5th, and then take the cube root of that. So if I have any rational exponent that actually represents taking a power and then taking a root, that represents some number. And there actually is a power of 2 that gives us 19. It's going to be between 2 to the 4th, which is 16, and 2 to the 5th, which is 32. And the actual power of 2 that gives you 19 to 7-digit accuracy is 4.247928. In the same way, we can write 33 as a power of 2. And then we can multiply 19 times 33 by adding these two powers of 2. That gives us 2 to the 9.292322. And if I've got a table of powers of 2, I can see that that's approximately 627. Since 19 times 33 is an integer, I know that it's got to be exactly 627. Now, if I look at that exponential equation, 2 to the 4.247928 equals 19. What is happening there, if I start with a 19 and I want to know what that exponent is, what Napier did was to call the exponent the logarithm of 19. Now, the number that we're exponentiating, that 2, is called the base. So 2 is the base, 4.247928 is the logarithm of 19 for the base 2. And the problem then becomes, given an integer, find the exponent of 2 that's going to lead to that integer. In other words, find the logarithm base 2. And then if you know the logarithm, if you know the exponent, what is the number that comes out of that? And so this introduces the idea of the exponential function. We're interested not just in 2 squared and 2 cubed and the integer powers of 2 or the simple fractional powers of 2. We're interested in 2 raised to a power that could be any real number. We're now interested in the exponential as a function. Now, in order to be able to do the kinds of calculations that Napier needed to do and that the astronomers, people like Kepler, needed to do, if we want 7-digit accuracy, then what we're going to need to be able to do is find tables of logarithms for all of the numbers in increments of 1 in 10 million. Now, I can simplify the problem slightly by just asking for the logarithms of the numbers between 1 and 10. If I know the logarithms of the numbers between 1 and 10, and I've got 2 numbers like 19 and 33, I can divide 19 by 10 and 33 by 10, and I'm taking the product of 1.9 times 3.3. And if I know that product, I take that answer and I just put the factors of 10 back in. So I'll take my answer and multiply it by 100. But this still is a problem of how to get the logarithms of the numbers from 1 to 10 down to the kind of accuracy that you need. And one of Napier's great insights is that if you know the logarithms for base 2, you can use them to find the logarithms for base 3 or any other base you want to use. That there is always going to be a simple conversion factor, so that if I calculate the logarithms for base 2, I can use them to find logarithms for base 3, or base 5, or base 10, or whatever base I might want to use. Now, a base that actually makes sense if you're going to do 7-digit accuracy is the base 1.0000001. So that's 1 plus 1 over 10 million. If I can find the logarithms for that base, and the powers of that base are fairly easy to calculate, if I want to multiply a number by 1.0000001, I just take that number and that same number with a decimal point moved over 7 places and add those two together. If I want to take those powers, that will give me the 7-digit accuracy that I need. But in order to get the logarithms for all the numbers from 1 to 10, I'm going to need 23 million powers of 1.0000001. Now, that's an impossible task, and Napier realized that he couldn't do those 23 million calculations. But his insight that once you know the logarithms for one base, there will always be a simple conversion factor that enables you to find the logarithms for any other base, actually enabled him to find these 23 million values very easily. What he actually did was to first find the powers of 1.01 that go from 1 up to 10. You only need 230 powers in order to accomplish that. And then what he did was to interpolate between those. So he then took the powers of 1.0005, 20 powers of that, enabled him to get numbers between 1 and 1.01, between 1.01 and 1.02, and so on. And then he looked at the first 50 powers of 1 plus 1 over 100,000, and that enabled him to interpolate between the values that he already had. And then he looked at the first 100 powers of 1 plus 1 over 10 million, and that enabled him to interpolate beyond the remaining powers. So with just a few hundred calculations, he was actually able to set up tables that would enable somebody to find logarithms to the base 1.00001 for all numbers between 1 and 10 to the desired 7-digit accuracy. But he also realized that since it was so easy to change these bases back and forth, there was no reason to stick with the base 1.0000001. He could choose any base he wanted. And so the question that he next grappled with is what base to use. And what he did was to consider two lines with points moving along each line. And on the first line, we've got the point that we want to take the logarithm of. So we're going to take the logarithm of a real number, and that real number is traveling along this first line. And on the second line, we look at the image of that point under the logarithm. So I've got a point like 3. On the second line, the position is going to be at the logarithm of 3. When the first point gets to 5, the point on the second line is moved up to the logarithm of 5. Get up to 13, it's moved up to the logarithm of 13. The point on the first line travels at a uniform speed. How fast does the point on the second line move? Well, what Napier realized is that the point on the second line moves at a speed that is inversely proportional to the distance that the point on the first line has moved. In other words, if the first point has moved to position x, the speed of the point on the second line is going to be some constant divided by x. The value of that constant is going to depend on the base that I am using for the logarithm. And what Napier decided was to choose the base that would give him a speed where that constant of proportionality was exactly equal to 1. Now, for those who know a little bit about calculus, you may have realized at this point that that's exactly equivalent to finding the slope of the derivative of the logarithm function, and that the slope of the derivative of the logarithmic function is inversely proportional to the value at which you're evaluating it, and that it is this particular logarithm that Napier chose that is what today we call the natural logarithm. Napier never actually worked out what that base needs to be, but it was later observed that it's a number between 2 and 3. It's about 2.71. It's a number that would later be referred to by the letter e, and e now is known as the base of the natural logarithm. It is the base of Napier's logarithm. The actual name natural logarithm would be invented later on in the 1600s. While Napier used this particular base, 2.71, Henry Briggs down in London got a hold of Napier's work on logarithms and recognized that a lot of the calculations would be much easier if instead of using this strange number 2.71, Napier would actually go back and use the base 10. If you're actually taking powers of numbers, a base 10 makes it much easier to work with. And so Briggs went up to Edinburgh in 1615, and he convinced Napier, instead of working out his table of values with 2.71 as the base, to use 10 as the base. Briggs would then go on to develop his own tables of logarithms, and in 1628, Briggs would actually publish a table of logarithms that was accurate to 10-digit accuracy. But Napier's logarithm, this 2.71 base, would wind up having a very important role to play in the calculus. And in the mid-17th century, two Belgian Jesuits, Gregorius St. Vincent and Alfonso Antonio de Sarasa, would consider the problem of finding the area underneath the curve of a hyperbola. So that's a curve that's simply the reciprocal of the variable, so the graph of y equals 1 over x. And what they were able to show is that if you look at the area underneath this curve, starting at x equals 1, going up to some value, say t, the area underneath the hyperbola from 1 to t is actually given by Napier's logarithm of t. It's given by this natural logarithm of t. And so we get both the exponential function and the logarithmic function coming in, and they would be very important concepts as mathematicians then went on to develop the calculus. I'll talk about that more in later lectures. But for the next lecture, I want to go back to the beginning of the 1600s and take a look at another one of the important influences of astronomy, and that is on the work of Galileo and the beginning of the understanding of the mathematics of motion.